I've given several presentations at the previous PM summits, benchmarking various types of persistent memory and comparing it to different types of storage using synthetic as well as real-world workloads. So today we're going to look at benchmarking and testing DCPMM, Optane Persistent Memory, NVDIMM-N. We're also going to compare that to XL Flash SSD, a TLC SSD, and a 3D Crosspoint Optane SSD. Those will be benchmarked against some synthetic corner case workloads as well as more real-world workloads in addition to the ones we've been showing. And in the second half, we're going to be looking at AI optimization using machine learning, and Yafei will talk about that. So this slide shows you a typical real-world workload. It's been shown before. I just wanted to refresh the people who have seen it, or for you who haven't seen it. What it shows you is that real-world workloads are a capture of IO stream activity that occurs in the software stack when you do something. So it's not a synthetic workload. It's not a random 4K write type thing. You actually capture the IO streams and metrics that occur when you do something in the software stack from point A to point B. So most often you're interested in what IOs are going to storage, but it can also be IOs going on one end of the wire to the other, or from virtual to hardware, or anywhere else you want to look. When you look at this picture, time is on the x-axis, and the y-axis is IOs, as well as queue depth in terms of users. So you see the three things you want to notice here. One, you have a constantly changing combination of IO streams. So when you look at those vertical bars, you can see a left-hand bar that spikes up over a 2 a.m. SQL Server backup with random and sequential 64K read writes. You can see morning boot storm activity with primarily sequential half K writes, and so on and so forth. You can also see the corresponding demand intensity or number of users in that orange line that goes across. So you can see that users vary depending on the time of day. You can have very few users in the early morning hours. It can spike during morning boot storm. It can go up and down during the course of the day. The third thing I want to draw your attention to is there are a number of IO streams. If you look at the cumulative IO workload box on the right, yes, the right side, it shows you that we've selected to show 9 of the most prominent IO streams, the ones that occur the most. But there are over 5,000 IO streams that occur over a 24-hour day. So not only are IO streams changing from moment to moment, there are many, many, many IO streams. So this obviously affects your performance, and looking at a real-world workload applied to storage gives you a very different look at how your storage is going to perform. The last thing on this slide is, depending on where you are in the stack, your workloads are going to be different. So the workload works its way down from user space to application space to the kernel to storage and back. And at each layer of abstraction, the IOs change. They can be coalesced, fragmented, merged, and so on and so forth. So when you want to test your X to a real-world workload, you want to make sure that you're pulling the workload from the right spot in the stack. So if you're in user space, you don't care what goes into storage. If you're at storage, it doesn't matter to you how many IOs are going to cache. I only care about how many IOs ultimately get down to me down at the storage level. Okay, so what are real-world workload use cases? They're pretty much everything. Today we're going to concentrate on AI-related workloads, so we're going to look at 5G edge storage, video edge storage, but we also have workloads from cloud storage servers, from web portals, and the like. Pretty much any use case involves or can benefit from real-world workloads, but simply put, in this case for AI, you're looking to gather raw data from the edge and transmit it in to process it and train with it. For cloud servers or data centers, you're looking to see the IO load to balance your IOs and see where the bottlenecks are and see how well their storage servers are being utilized. Okay, so this graphic shows you real-world workloads going out to a bunch of different architectures. The main point of this slide is just to show you that this is a disaggregated capture and test architecture. That means that you can capture the IOs anywhere in the wild, at the file system level, at the virtual level. You can do it on the virtual storage servers, physical storage servers, to direct attached storage, to any virtual storage or logical storage. Equally, once you have a capture and you curate it, you can take the workload and then apply the workload to test storage at any level that you see. It can be logical or virtual. So what does an IO workload, an IO capture workload look like, and what does it do? This slide kind of looks at the life cycle of an IO capture. So what's an IO capture versus an IO trace? So we're all familiar with IO traces. You have block trace and others, and it's a constant collection of continuous data, and it results in a humongous file size. So they're difficult to process, they're huge in size, they're difficult to transfer. An I/O capture or an I/O profile real-world workload captures the statistics about the I/O streams that occur from moment to moment. So it's a time-stepped capture, which means that you can set the resolution to 1 millisecond or 1 second or 1 minute, and you can average all of the I/Os over that period and make a table of statistics about those I/Os. So instead of capturing 400,000 random 4K writes and saving them to look at it, you can have a table that says, I saw 400,000 random 4K writes and they had these characteristics. So by making a binary table, you aren't taking any personal data, you're reducing the file size so I can easily port it to wherever I want to go, and then when you get it, you can rebuild your workload on a time basis, moment to moment, and recreate the workload that you had. So in item 2, you're seeing edge transmission of these workloads from your IoT devices or your edge servers. It can go to your AI data center. It can be a constant stream of data packets if you want, or it can be transferred as a whole file. You can use I/O captures to do continuous monitoring of the edge workloads. So if you're doing the AI and you've done your training and inference, you can still be grabbing real-world workloads in real time to monitor if the edge traffic is still the same as the basis upon which you did your inference. So in other words, if I train it to do ABC, I want to make sure I'm still getting ABC and not 1, 2, 3. As far as what you get, you have a wealth of key performance indicators from I/O, bandwidth, response times, process IDs, pretty much whatever you want to capture. And again, those are captured as statistics and tables, and they're easily curated, so you can take your workload, you can filter it or parse it to get what is of interest to you, and then you can take that and create a replay training workload that can be applied for AI, or you can do it to test your storage servers for qualification or validation. Okay, so in the AI world, what we're interested in is getting the data. All AI is pretty much based on I can get enough data. So how do you get that data? So again, capturing data from the edge is very difficult because the files are too big to be useful to be used in real time. If you use the I/O capture workload, you can get these workloads streaming to you. They can be in very small tables. They can be rebuilt in the database, and they can be curated to whatever you want to look for. In the case of AI, you typically look at things for machine learning in this trifecta here called gather, training, and inference. So gather is merely the activity of collecting the workloads from the edge. So the I/O capture tool versus I/O trace is very effective for this. The inset box that you can't see clearly here, but when you download you can look at it, is a LSTM, or a long short-term memory recurrent neural network graph showing you the input and output. The middle part, which is the LSTM, Yafei will speak to, but you can capture the raw IOs going into it. You can then capture the data coming out after LSTM, and you can look at those workloads to assess their performance. In the training, you can take the workload that you curated, and then you can create replay tests and run a loop of training tests to your storage and use that in the course of developing your AI optimization algorithms. And then as far as the inference is confirmed, you can look at how well your performance is with that same raw workload, at the same time monitoring the edge traffic to confirm that I'm still looking at optimizing ABC traffic instead of 1, 2, 3. Okay, so we're going to look at a couple of real-world workloads, and when you look at this picture, you can see that when you glance at them, they look different, right? The I/O streams are bars or continuous hash or horizontal. You can look at I/O clustering. The point of this slide is to show you that workloads can show you different key performance indicators. You can look at the I/O stream consistency. You can look at I/O and response time spikes. You can look at IOPS and throughputs. You can look at quality of service, a variety of metrics. So when I look at these, you can see that on the left, I've got retail web portal, which is based on different kinds of activity and different kinds of IOs. On the middle, I can see boot a C drive with a lot of cache activity being dominated by 128-byte reads. And on the right, you can see a more consistent pattern of labeled data that shows up as a random 4K, 8K, 16K type workload that we expect to see in corner case testing. Okay, so we're going to look at some reference workloads, and you can look at this table offline to see more details about it, but I just wanted to show you a couple of things. One, we use a synthetic database as a baseline test, which is basically a simple synthetic application of random 8K read-write with 65% reads. The next 4 are real-world workloads. One's a retail web portal, one's a GPS nav portal, one is data center storage, and the last one is video on demand edge server. When you look at the red column, the first one, that's the overall read-write mix. So you can glance at these previous I/O streams, and there are all these points and bars and lines that might look confusing, but at a very high level, you can see that some are 65% read, 96% write, 75% read, 60% read. Similarly, if you look at the min, median, and max queue depth range, you can see that the median queue depth can be 23, 8, 62, or 3, and the max queue depth can range from 42 to 306. And then finally, on the right-hand side, you can see what the main I/O streams are. So for the second workload, it's 64K, half K, 8K, 4K. The next one is 4K, half K, 16K, 1K, and so on and so forth. Now again, these are the main I/O streams that we selected. Of course, there's hundreds of I/O streams, but these 4 or 5 or 10 might represent 80 or 90% of the workload, and those are the ones that we're interested in seeing. And then finally, on the right-hand side, you can see the access, whether it's a random or sequential access, and some are more random and some are more sequential. So, getting to the test sample pool, we're going to look at Intel DCPMM, the persistent memory. We're going to look at an NVDIMM-N. And then we're also going to look at a SLC flash drive. We're going to look at a 3D XPoint SSD. And we're going to look at a TLC NVMe SSD. So the 3 SSDs are all NVMe SSDs. And the 2 DIMMs at the bottom are Optane, DCPMM, and NVDIMM-N. Okay. As far as how we're going to test them, you've seen variations of this chart in all the previous presentations. So basically, we're going to apply the workloads through the file system to the SSDs for the SSDs, and through a PM-aware file system using the PM driver to the persistent memory. Okay. This is a summary of all the data you're going to see in the next 4 charts. But to put it simply, we've got persistent memory, there's data center PMM and NVDIMMs being compared. And on the right-hand side, you've got NVMe SSDs. The XL flash is looked at just for a few corner case workloads, and the 3D XPoint and the TLC NAND are compared against all the workloads. For the synthetic corner case, for the DCPMM and NVDIMM, we're just going to apply a 64-byte, 128-byte, 256-byte, or 512-byte random or sequential read-write workload. So the first line is going to be reads, and the second line is writes. So before you see the charts, DCPM has faster sequential reads and slower random writes. Conversely, the NVDIMM showed slower sequential reads and faster random writes. So we'll show a couple of plots that show that. As far as the corner case for the SSDs, looking at the I/O rate and the bandwidth, you can see that the XL SLC had the fastest random 4K read IOPS. The 3D XPoint had the fastest random 4K write IOPS, and the TLC 3D NAND had the fastest sequential 128K bandwidth. You're going to see more detail in the charts, but the main thing about this chart at the top, it says performance depends on the workload. So we're comparing very different classes of storage with very different workloads. So in some cases, some test samples are better than others. In other cases, they're not. And it really depends on the workload. And some of the workloads that we use from the real world are more suited for NVMe SSDs. Others are more suited for persistent memory. So keep that in mind. Performance always depends on the workload. For the middle line and the bottom row, these are the real world workloads. So for the real world workloads, if we make a synthetic test out of it, it has these multiple I/O streams. You can use those multiple I/O streams and apply them for every step of the test and make a synthetic test. So for example, if we had a random 4K read-write workload, 50-50, we could do every step of the test 50-50 random 4K, and that would be a synthetic workload test. If in the real world the first half hour was all reads and the second was all writes, that would be a real world replay workload. So in both cases, at the end of the test, you have 50-50 4K read-write, but in the first case, every step was 50-50 4K read-write. In the second case, the first half was reads and the second half was writes. So in that case, the performance average may be the same, but if you have hundreds of different I/O streams, you can see that you'll have a difference between having the same percentage for each step of the test in a synthetic test versus varying between backup to morning boot storm and so forth as you go along. Excuse me. So the final takeaway is when you look at the ordinal ranking, there's only 2 drives. There's 2 drives for the persistent memory and the 2 drives for the NVMe SSD or the 3D XPoint and the TLC NAND. So the red numbers are IOPS and the blue numbers are average response time. So just glancing at it, you can see that in some cases for some workloads, one drive is better than the other, vice versa for the other. For the response times, they tend to be more uniform, that regardless of the I/O streams, the response times generally rank the same. So if it has faster response times, it'll tend to be faster despite what the I/O streams are, but I can have different I/O rates depending on what the workload is. Okay. So we said for persistent memory, sequential read-write benchmarks, 64-byte, 128-byte, 256-byte, and 512-byte. These are, on the left side, sequential reads, on the right side, sequential writes. So you can see the yellow bar is higher. Higher IOPS are better. That's DCPMM. The green bars are NVDIMM-N. So from an IOPS point of view, the persistent memory is faster for sequential read-write. For response times, you can see the response times are substantially similar until you get to a larger block size like 512-byte, in which case the NVDIMM has lower response time than the DCPMM. Looking at random read-write, the same way, you can see for random reads, they're pretty close. Even though NVDIMM, the green bar, is better for 64 and then less for the other 3, they're a substantially similar range. But note that the average response times for random reads, the NVDIMM is lower than the DCPMM. On the right-hand side, we're looking at random writes. Here, clearly, the green bars are higher. So you're seeing superior or faster performance of NVDIMM-Ns against DCPMM for random writes. Again, for response times, you can see that the NVDIMM has better response times. So when you look at those bottom ordinal ranking boxes on the right-hand side, the very bottom line says 1111. Average response time for NVDIMM-Ns is faster for all block sizes. For IOPS, it's first. Very simple one. On the left-hand side, it's 1111 in response time, but 1222 in IOPS. So again, the response times are consistent, but the I/O rate can be up or down. And in this case, they're not significantly different. Okay, let's look at the SSDs. So for the SSDs, we're using the SNIA IOPS test and the SNIA throughput test. On the left-hand side, and you can see the IOPS, red is writes, blue is reads. So for the TLC NVMe SSD, it has second place for the red. The middle XL flash is third place, and the right-hand side 3D XPoint has the highest performance for random 4K writes. For random 4K reads, the middle blue bar is the highest, and that's the XL flash. The second is the TLC NVMe, and third is the 3D XPoint. But when you look at the overall performance, the 3D XPoint is very symmetric. The reads and writes are about the same, and they're pretty high. So it kind of depends on what your workload is, what you really need. For throughput, you can see that in this case, the NVMe SSD has pretty balanced reads and writes. Again, the SLC XL flash has faster reads than writes, and then the 3D XPoint is fairly symmetric as well. So again, these are corner case tests with this particular workload, but I again hazard to tell you that the media is designed for different kinds of workloads and different kinds of demand intensity, but this is just a corner case test that gives you a relative ranking. For the read latency, we're just looking at an outstanding I/O of 1. What's the response time of a single I/O round trip? So we express that as thread count 1, queue depth 1, or T1, Q1. So you can see here that as expected, NVMe SSDs have about 100 milliseconds response time. This is read latency. So you can see for random reads, you have 99, and for sequential reads, you have 92. 3D XPoint is known to be very fast, and it's around 10 to 13 microseconds. So in the case of the random reads on the left, it's 11.9, and on the right for sequential, it's 11.2. And the driver really of interest here is the SLC XL flash drive in the middle. And it shows 20 microseconds and 13.5 microseconds, which is really very good. So the published spec for XL flash is 25 microseconds for read latency. So in this particular case, it outperformed what was in the public domain. This is the synthetic view of those real-world workloads. So we took the top 9 I/O streams and applied that ratio of I/O streams for every step across. It was like, remember the random 4K read-write example? Every step is 50% reads, 50% writes. So in this case, for each of the workloads, we're applying a constant workload to it. So looking first at just the green and the green and yellow bars, this is your NVDIMM-N green and your DCPMM yellow. So you can see first off that they are much, much higher IOPS and much, much lower response times than the corresponding SSDs, which is red and blue. So for the Optane, you can see that it has 1 million, 1,000,004, 600, 600, and 148 IOPS for those particular workloads. And the NVDIMM is faster for the synthetic random AK 6535, slower for the VDI storage and the retail web, but faster for the GPS nav and faster for the video on demand edge server. So you can go back and look at the box and the description of the workloads, and it might be faster because it's more write intensive, or it might be faster because it has more reads. You know, it just really depends on the workload. For the for the NVMe SSD and the Optane SSD, the Optane is the red, so he's faster for the synthetic than for the video on demand and the retail web. It's slower, but then he's faster for the GPS nav and slower for the edge server. In terms of response times, you can see that the NVDIMM is faster than the DCPM on these particular workloads. Now again, these workloads are captured. They're comprised of very large block sizes and transfers, and these are not particularly the type of workloads that you would see in a persistent memory architecture. But having said that, the IOs are what they are, but in terms of response time, you can see the NVDIMM-N has faster response times for all of those particular workloads. In the same case, the 3D XPoint has faster response times than the NVMe SSD. So that's an expected behavior. In the first case, it's probably workload dependent. And then this is the same look at those 4 workloads, but as a replay. So here we replay the sequence of the IO streams that we observed. So it can start out with SQL Server backup, then do morning boot storm, then do mixed IOs for working hours. So when you look at this for the VDI storage, again, Optane is faster than NVDIMM, but in the next 3 cases, NVDIMM is faster than the DCPM. For the SSDs, the red 3D XPoint is slower for the first 3 and faster for the last, but they're pretty close to the TLC NVMe SSD. So it's kind of interesting that the NVMe SSD has faster performance than a 3D XPoint SSD. But again, it's just for these particular workloads. When you look at it from a response time point of view, you see what you expect is that the 3D XPoint has faster response times than the NVMe SSD. Again, for the Optane and the NVDIMM-N, the NVDIMM-N shows slightly faster response times. So I'm sure you're very excited to see all these graphs and charts. You can look online to compare. But the main point of this is you should be careful when you benchmark any storage, because storage is designed for a particular workload. So you should know what your workload is and then use that workload to characterize your storage. I can find a workload that can make any drive look pretty good on any given day. So it's really all about the workload. So at this point, I'm going to hand it over to Yafei, and he's going to talk about performance tuning. Right, it's forward.
Okay. Thanks, Eden. Hello, everyone. My name is Yafei, and I'm from DapuStor.
Move your mic up just slightly.
You have to turn it on the box.
It's on, right? I thought it's on. Right?
No, it's there.
Oh, okay.
It's like in
it's
China,
on,
the
right?
slide advances on.
Okay, thanks. So my name is Yafei, and I'm from DapuStor. We place intelligence inside the NVM devices. Eden, you have eaten up my time, so I will go fast. But but you have the real meat. So I started to work with Eden a while ago, and we have made a good progress on the SSD performance tuning with the real workload. So in my part, I will talk about how we utilize the artificial intelligence and the machine learning and with the real workload to optimize the XL flash SSD. So what is XL flash? XL flash is SLC 3D NAND flash memory, focusing on the low latency. It's offered by the Kyocera, and formerly that is the Toshiba Memory Corporation. Compared with the TLC, it has much lower latency. The TR is only 5 microseconds, and it has a high endurance. And more important for us, it has the compatible packages, and it's easy for us to port to the existing SSD controller. And based on the latency performance, we can put in this order, right? So from the left to right, DRAM, Optane, XL flash SSD, TLC SSD, HDD, and tape. And from right to left, higher cost, lower capacity, and lower latency. What's that? Okay. So here, we use the real workload to compare the XL flash SSD and the TLC SSD. So you can see here, we use the same controller and the same firmware architecture. And most of the firmware code are the same. So you can see that in general, the XL flash SSD is much better than the TLC SSD. As we all know that it's big challenge for performing performance tuning on the NVMe devices, because it's an embedded system and you have to make the tools to do the troubleshooting. And also there are many dimensions you have to consider in the target, such as IOPS, queues, low latency, reliability, etc. And more important, it's hard to get the real workload from the user cases. SNIA has provided some very good benchmarks and I/O traces, which are very helpful. But we have to face the complex workloads from the commercial world. So normally there are always some workloads you cannot handle. And so that's why we started to think about how we perform the tuning. And is there a better way to do that? We thought it might be a good idea to put intelligence into the devices and make those devices smarter enough to predict IOs from the host side. So if the devices can do such job, the devices can have dynamic strategies and it can return better performance. So we have explored different methods, including neural networks and machine learnings. And finally, we found LSTM is a good technology to do this job. LSTM stands for the long short-term memory. Is one kind of the recurrent neural networks, and LSTM has been applied in various applications such as weather forecast, language modeling, etc. And it's good to handle the time series problem. Since the storage I/O prediction is also a time series problem, so we use LSTM to do the storage I/O prediction. But the major challenge of using LSTM is the computation complex. So in this case, you cannot just apply this technology to the existing controller. So you have to make a special hardware. So that's why we made the FPGA to do the work. So you see that from the LSTM there are multiple layers, the input layer, the hidden layer, the output layers. And inside each layer, there are many cells. And inside one cell, you can see there are 4 gates: the input gate, cell gate, forget gate, and output gate. The 4 gates decide which states should stay and which should be forgotten. And in our proposed model, the input layer, we have 4 cells, which are the I/O, the I/O address, the length, the read-write ratio, and the read-write interval. And the output has 1 cell, which is I/O intensity. That is the output we want. And we implemented the FPGA-based SSD, and we got very good results. So the I/O we got is from the SNIA and also the real world. And so you can see that the red curve is real I/O intensity, and the blue one is a prediction result. So it matches very well. But again, it needs compute. And normally, the existing SSD or NVM devices do not have such compute capability. So in order to make this technology commercial, to make it popular, so you have to make an ASIC chip, including this LSTM IP. That's one way to go. The other way, we thought maybe we can do something lightweight on the software level. So we did such work, and we implement the firmware level, the reinforcement learning algorithm. So this chart shows a performance tuning framework. You can see that the green one is LSTM hardware, and the red one is the machine learning embedded C library. So they are separate. We need either of them to do the prediction job. As long as the device has a prediction capability, it can do a lot of things. It can do it has a smart cache policy, the smart GC policy, and also it can do the on-the-fly queues management, etc. So now we have 2 effective approaches, software solution and hardware solution. So what are the differences? So from the response time perspective, the hardware is a nanosecond level, and the software is a microsecond level. And from the predict window, you can see that hardware can do the millisecond, and the software only does the second level, which means granularity is different. And the predict performance, the hardware is better than the software. So since hardware, next step for us is to have a ASIC test chip, including this IP this year. And the software we have implemented, and we team up with Marvell and Kioxia together. And for Marvell, we use their latest enterprise SSD controller, which is ZAO. And we got XL flash samples from Kioxia. Here, you see that the left one is without machine learning optimization. The right one is with machine learning enabled. So you can see that the improvement is around like 20%. And again, the workload that we use is from Eden. This is real one and a mix of read and write I/O streams. So generally speaking, so we think we are on the right track to ask the device to predict the I/Os from the host. And but hardware, it needs compute, and the software, so far the improvement is not so much, but we are still working on that. This project is like a work in progress. And here I'd like to call more collaboration and partnership. So if you are interested, please talk to us. So maybe later we can together to do the more intelligence work here. This concludes my talk.
We're a little bit behind, but does anybody have any questions for DapuStor? All right, we have, where? There we go. Why don't you get Tom and Jim mic'd up while we answer this question?
Yeah. Good. Okay.
Thank you for your interesting presentation. So after the drive predicts the workload, what are the actions that the drive takes, based on the predicted results?
Okay, there are different ways to. So first, we need to get the I/O intensity, right? Once we get that, we know the I/O flows. We know whether it's like a 4K I/O or it's like a 512 bytes. And then we can design the cache. So basically, the cache can be divided to write and read, right? Pre-read or the write. So if you don't know that, then you have to fix the cache. But if you know this dynamically, then you can assign, cache to read or write. That's one way, to do this smart thing.
Great, excellent. Thank you. Give them one more hand.